with others. So thank you for coming to the TARC mentoring session. Oh, it's doing live transcriptions. It's exciting. We're going to go over how to make some basic shapes to help build your TARC rocket using OnShape. And the first thing I wanted to go over is that if you don't have an account, just Google OnShape free account for students, and you should get to this page right here. So you can sign up for your own free OnShape account. Now, those of you who are joining us from a homeschool group, list the school you would be attending if you were going to public school. So if you would normally be going to Elkins High School, list that as your school. I'm pretty sure that most of these systems have a database of schools, and they say, oh, okay, you are the right age, you are a student, this is your school, check, and it'll let you have an account. It shouldn't be difficult to do. Once you've created your account, then you get to this page right here, which is OnShape, and you'll click on the top right corner, sign in. It's not important you follow along with me right now. What's important is that you take some notes. Maybe if you want to try something out, that's great. But basically, what's really important is that you take some observations and notes. The next thing that we want to do is we want to open up apogeerockets.com, because using measurements are critical to the success of this program. And I often need measurements. So the measurement that I need right now is that I'm going to build something simple. I'm going to build a engine tube and a centering ring. So we'll start from the bottom of your rocket. So the body tube on your rocket is a BT80, correct? Yes, Todd. So I'm going to go to building supplies. I'm going to go to body tubes, and I'm going to look for 56 to 98 millimeter tubes. I'm going to scroll down until I find the standard BT80 right here. Okay, now the reason I like this website is, drum roll, this little box right here. Tim Van Mulligan, also known as the Rocket Guy, I think Rocket Man, he takes very careful measurements and uses those and publishes them on his website. So I need to know the inner diameter of a BT80 tube in order for me to make my next series of parts. So it's 65 millimeters. So note number one, make your OnShape account. Number two, everything you do should be in millimeters. Every 3D printer I've ever worked with in my life defaults to millimeters. So please just get used to dealing with that. 2.58 centimeters is 1 inch. Write that down. 2.58 centimeters or 25.8 millimeters is an inch. Or is it 25.4? Someone check me on that. Someone Google that. I think it's 25.4, 25.8. So what we're going to do is we are going to create a engine tube and a centering ring. So to create a new part, I hit create on the top left. I hit document. I'm going to call this a 29 millimeter engine tube. I'm going to say demo just because I know what it is. Now, with an engine, I assume you're all going to use 29 millimeter engines. I have a free tip. If you're not using a 29 millimeter engine, you might use a 24. Still build your rocket with a 29 millimeter motor mount. Why? Anyone know why? Anyone? Bueller? Why would I always build a 29 millimeter motor mount, even if I'm going to use a 24-inch motor? I'm sorry, 24 millimeter motor. Any ideas why? Can you put a 29 millimeter motor in a 24-inch engine tube?
No, sir, the motor is too large.
It will not work, but you can put a 24-inch engine in a 29 millimeter tube with a small adapter. So you can print a 29 millimeter, 24 millimeter adapter, even if you have any rocket. So always build with a larger rocket engine diameter and step it down with an adapter if you need to. Okay, the first thing I do when I'm designing this engine tube is I'm going to click on the top work plane. There's 3 work planes, top, front, and right. Okay, I like to also hit this little orientation box and center myself up. Then there's a button right here, and this is if you've never used 3D CAD tools, they all have the same basic functionality. You start with work planes, you sketch out what you want in 2 dimensions, and then you make it 3-dimensional. And if you want some icing on the cake, you can then tweak your 3-dimensional object. But first thing I'm gonna do is click the sketch button. Okay. Now a whole palette of tools popped up that were not there before. Okay. These tools are basic shapes: lines, squares, circles, arcs, inscribed polygons, splines, etc. What I'm going to do is I'm going to choose circle, and there's a variety of circles. I want center point circle. That's the default one. I'm going to click inside on the origin and start to draw my circle. Again, you don't have to do this right now, but just note, I tap with my mouse button once. And when I do that, I have no idea what the measurement is right now. It's 53 millimeters, but by clicking once, it enters an edit mode. Now the diameter of the engine I'm going to put in that is 29. If I make this exactly 29, it'll be a tight fit. You may not get your engine in and out of your engine tube. So I'm going to go 29.1. So I type those numbers to my keyboard. I press the enter button. I've now made a 29.1 millimeter circle. I'm going to do that again. I already have the center circle button on. I click, I drag. Now here's where you need to do some math. How thick of a wall do you think we want on an engine tube? What is your guess?
0.61 millimeters.
How many millimeters would you like?
0.61.
So that's if you were doing a paper tube, right? That's what you're looking at, the measurements off of apogee rockets. So we're not doing a paper tube, we're doing a plastic tube. If you do a 1 millimeter thick tube, you could crush it with your hand easily. You could break it. That's probably not strong enough. So 3 millimeters is a little overkill for a tube. So I'm going to suggest 2. So if we had a 29 millimeter hole in the middle, I realize it's 29.1, and we put a 2 millimeter thick wall on each side around this, okay? So it's not 29 plus 2, it's 29 plus 4 to get the diameter, the outer diameter of this tube. So 29, 30, 31, 32, 33. So 33 millimeters is going to be the outer diameter of my engine tube. So that's just slightly less than 2 millimeter thick walls. When I'm done with a sketch, I click the green checkbox. That means I'm done sketching. Over here on the orientation box, I'm going to say isometric so I can see it. Now the palette of tools has changed again. These are all tools that affect a 2-dimensional object and turn it 3-dimensional. The most commonly used tool is, anyone? Extrude. I click extrude and it defaults to making a new material. It's going to add new material, solid, and it says, give me a shape. What do you want to extrude? So what I want to extrude is the space between these 2 circles. I click on that space and it extrudes it out. Now, extrude is like squirting something out of a shape. I don't know if you ever played with like a Play-Doh when you were a kid. But my kid had a Play-Doh device where you'd shove Play-Doh into a little piston. You put different shapes like a triangle, a circle, or whatever, and then when you push it, it would squirt out the Play-Doh in that shape. Okay, if you haven't seen that, I'm assuming you've all brushed your teeth. When you squirt your toothpaste out, it comes out in a cylinder, right? It's not a cylinder inside the toothpaste tube. It's just coming out of a round circle opening. And so we're extruding or squeezing material out. Ironically, this is what a 3D printer does to a certain extent. It extrudes out a tiny little nozzle of plastic. Now it says, my default guess, the software is guessing, 25 millimeters high. I'm telling you right now that that's not big enough for your engine. Most engines, if you start looking them up, your F engines are going to be at least 70, 80 millimeters. Let's say 100 millimeters. I've now created a cylinder that is 100 millimeters long. I'm going to click the green checkbox again. That was it. We did it. We drew 2 circles and we extruded it. 3 steps. Actually, really only 2 steps. For those of you who have not done 3D CAD before, what do you think? Is this easy? Is it scary? Is it confusing? Simple? How are you feeling?
It looks pretty simple.
Pretty straightforward, huh?
Yeah.
Now, let me show you how do you get this to a 3D printer. I have a part, and because we're on OnShape, it's already saved. Down here is our feature tree. It shows us all of our work planes. It shows us our sketch that we made. It shows us the feature we did called an extrusion. And then down below, it shows 3-dimensional parts that were created. I click on that part. See how the whole part's highlighted? I'm going to right click on that part, and one of the options says export. If I export it, it says, what do you want to call it? I'm going to call this an engine tube. 29 millimeter. The format is STL, and that's what 3D printers are going to read. Okay, units are millimeters. Resolution. Now, this is a critical thing here. Not all software works the same, but if you are drawing a cube, it's just all 90-degree angles. You could go in coarse resolution because an STL file is made of triangles. And a cube would have 2 triangles on one side, 2 triangles on the other side. It could have the lowest resolution. But when you have a circular object, if you don't have it set on fine resolution, it's not going to look like a circle. I'm not sure how many facets you would see, but it would be like a quartz crystal. You ever seen a quartz crystal has hexagonal geometry? It has 6 sides on a quartz crystal. I don't know if this makes sense. Have you ever seen salt zoomed in? Salt has also is cubic. There's shapes to it. So we don't want the flat sides in a circle. So choose fine resolution. And it says download. So I'll go ahead and export. And that should create the part. It downloads it. And if I look in my downloaded files, I will see it. I'm now at this point, I think you might not see what I'm looking at. So I can open that file up. I downloaded it to my computer. So that's how I get the shape I designed out as an STL. Any questions? Let's make a new part. Okay, I now have the engine tube to stick my engine in, but I'm going to create the centering rings. These are going to be BT80, and they're going to be 33 inner diameter. 33 inner diameter reflects the engine tube they're going to connect to. Now, if you were lost last time, watch quickly. I'm going to click on the work plane. I'm going to square up to the work plane. I'm going to go to the sketching tool. I'm going to go to the circle tool. Centered is default already. Okay, I'm going to draw a circle. Now, the inner circle is going to be 33. That's the exact dimension of the outside diameter of my engine tube. And a minute ago, I just said to you, if we're doing an engine tube, make sure it's a little bit bigger so our engine slide in. I want this to be a tight fit. I want this to be super snug. In fact, if it's too snug, I can just sand it a little bit. I'm not worried about it being a little bit too snug. I'm worried about being too loose. So if you make the exact measurement, 33 outside, 33 inside, it should be a tight fit, and a little bit of super glue is going to fuse those things together rock solid. So that's going to be my inner diameter. I'm going to make another circle. I'm going to make this one from the origin also, draw it out. Now, how big is it going to be? That's a good question. What was the pop quiz inner diameter of our BT80 body tube? Want to see that? 65 millimeters.
It was 6.5 millimeters.
So I'm going to type in here 65 millimeters. Again, I want a tight fit. Okay, I'm done. The green checkbox. Let's look at the isometric, which is three-dimensional view. Let's go to our extrude, the first button right after sketch. It says, what do you want to extrude, Todd? I click on the space between those two. It says, I'm just going to guess, my standard guess, 25 millimeters thick. Do you think this looks like a good centering ring to you?
Yes.
Okay, let's go to Apogee. Okay. Let's go to another Apogee page. Let's look at a centering ring. If you've built a rocket before, usually it's out of a piece of plywood, thin plywood. So shop, we're going to go to building supplies. We're going to go to centering rings. Let's look at a centering ring for this kind of thing here. We are looking at a BT60, BT80 body centering rings. Okay, this is a centering ring for a 24 millimeter, 24 millimeter. It doesn't really matter. I'm just looking for the thickness. Okay, thickness. 3.2 millimeters. So these are a thin piece of wood. So back to my drawing, that's 25 millimeters. So what do you guys think we should do for our thickness of our centering ring? We're making that in 3D plastic.
Bring it down.
This is the audience participation part of the class. I'm gonna suggest to you 3 is fine. If you want to do 3.2, it's fine. If you want to do 4, you're getting a little thick, a little carried away. If you did any more than 4, it's excessive, I would say. If you did it if you did 2, I've broken them. They've destroyed. So 2 millimeters is fine for our cylinder. 3 millimeters is what I recommend for a centering ring. So I've extruded it. I hit the checkbox. I export it out by right-clicking. I click on the part. I right-click on it. I say export. STL, fine. I give a name. This is my BT80 center ring for 29 millimeter engine tube. Export it out. Saved. Done. Questions so far? How are we doing? Question.
So you said that it can't go below 2, right, for the center rings?
I'm giving you Todd's free tip that 2 centimeters in the reality of 3D plastic parts is a little too thin. It breaks. I would suggest 3 millimeters. If you want to do 3.2, which was the exact measurement of this part right here, this wooden one, that would be fine. 4 is probably a little excessive, but I mean, you can, if you want to add weight to your rocket, you can do 4. If you're doing more than 4, I think you're getting a little carried away.
All right, thank you.
Sure. I'm not sure what's harder or easier next. I think they're both the same. I think I'll probably do a nose cone next. So we are using a BT70 body tube for our nose cone, correct? I'm sorry, for our payload bay. So what I'm going to do is let's pull up this Apogee rockets. Let's go back 1 page. Let's find our BT70 body tube. Here it is. Here's my measurements. The inner diameter is 55.4. My outer diameter is 56, apparently. Okay, so these are important measurements for us to know to make our nose cone. So we'll go back to OnShape. I'm going to make a new part. Click on the word OnShape, click Create, click Document. This is going to be a BT70 nose cone. Now I'm going to need your help with me. I have some math to do. I'm going to work with the front work plane. I'm going to square up to the front. I'm going to click my sketching tool. We are going to create half of a nose cone. A bilateral, I'm going to cut it right down the top. Okay. The first thing I'm going to start with is the very bottom. And this part I can start without too much guesswork. I know that my BT70 inner diameter is 55.4. Can someone tell me what is half of 55.4?
27.7.
Great. So I'm going to go to my line tool. See this little line tool? Click on that. I'm going to go to the origin. I'm going to snap. I'm going to start drawing my line. It doesn't matter what I do because I'm going to tap once my mouse. I'm going to type in the number. You said 27.7?
Yes, sir.
Enter. I made a line, 27.7. It shows the dimension there. This is 1/2 of the part of the nose cone that's called the shoulder that will slide in to the body tube. I recommend that you go up at least an inch. It's 25.4. My brain was glitching before. 25.4 is 1 inch, right? So let's just say I go up, 26 millimeters. It doesn't really matter, but something along those lines, we'll do 25.4 to be exact, 1 inch. So 25.4 is exactly 1 inch in millimeters. So that's how high up. This is the shoulder that's going to slide in. Now, I like to give at least a 1 millimeter lip here. So I click on the button right here. I type 1. There's that little tiny lip. Now I'm going to press the escape button and let go of this line. The next part is how tall of a nose cone do I want? Question. How tall can your 3D printer go? Anyone know? That's the limiting factor here. Now, if we looked at Apogee rockets and we said, okay, give me a nose cone example so that I have some idea of what a common nose cone is going to look like. Apogee rocket seems slow today. Go. 24 millimeter tubes to 54, 56. Okay, so I think that's us right there. Here's a BT70 nose cone right here. So how long is the shoulder? They say it's 58 millimeters. Too long. And they say the length is 267 millimeters. I'm just moving the decimal place one place over. 26.6 centimeters, 267 centimeters. That would make a nose cone. So if your 3D printer can handle that, that's great. Don't forget to include your shoulder as well in the total height of what your 3D printer is capable of. This is a limiting factor you'll have to know for yourself. I can't tell you what your 3D printer's limiting factor is. I'm going to click on the line tool. I'm going to start drawing a line from the origin straight up. Okay, and so I'm going to press escape again. Actually, no, I'm going to have to have a number. 250 millimeters. And now I'll press escape. So what I've got now is I have a shoulder And then I have this tall nose cone area. And you're probably thinking, I don't get it, Todd. It does not look like a rocket to me yet. What I'm going to do next is I'm going to zoom in on that little dot where I have that 1-inch lip. I'm going to look through my tools for drawing. I have line, I have rectangles, I have circles, I have arcs. Arc sounds cool. In my arcs, I have 3-point, tangent, center point, elliptical, conical. I'm going to try a 3-point arc. I'm going to click 1 point of my 3 points on that outside little lip of that 1 millimeter. I'm going to click the other dot of my 3-dot arc on the tip of my nose cone, which is that other end of that line I just drew. Now my third point is the one where I'm going to figure out where to put it. Up to me where I put that. So I can control the shape of my nose cone right now. I can have it look like the top of a Russian church. I can have it, you know, scoop in like that, what looks really pointy. I can have it kind of linear. I can have it kind of curved out from whichever point I want. I kind of like, this is looking good to me. This is not a measurement right now. I'm just doing it by feel, but I did a 3-point curve. Can everyone see how this shape just colored itself in? It's now like filled in gray. That means the software is telling you, you have a shape with all the sides closed. In other words, I don't have an opening anymore. This is a shape that can be manipulated in CAD. If I failed to touch 2 dots and I had a space between them, this would not fill in, and I would be in a bad place right now. I have to go figure out where I missed. I have to probably do an undo button. There's an undo button right over here. So if you mess up, undo is your friend. I'm gonna click the checkbox. So now I have this 2-dimensional half profile of a nose cone. Does anybody know what I'm gonna do to make this a nose cone that I can put in my rocket yet? Do you know what feature I'm gonna use? Extrude, revolve, sweep, loft, thicken. Any one of these?
Extrude.
The answer is revolve. Click on revolve, and it says, okay, Todd, what shape are we revolving? Give me the profile that I'm going to revolve. And I choose this shape. Then there's a red box that pops up and it says, give me the axis. What am I revolving around? And I'm going to click on the very long axis of the middle here. Oops, didn't do it. Faces, axis, and then faces. Like I said, I have to click on the box and tell it. So I click on the face, and then I click on the axis, and it says, oh, I think that you want to make a shape like this. Does anyone see how this is now a nose cone? And you can see kind of interestingly, there's that little profile, and then it's spun around this long axis right here. I click the checkbox, it's great. Now, the one problem I have is, this is a solid plastic nose cone right now, like literally filled with plastic. This would be a little too heavy for us. So I'm going to spin this around using my navigation tool. I'm going to click on the bottom. So I've now highlighted the bottom of this nose cone. And look at these features. I have additional features that I can apply to already dimensioned objects that are 3D. I can curve the edges. I can shave off the edges. I can draft, rib. That one sounds cool. Shell solid. Click that. It says, Todd, how thick of a wall do you want? It defaults to 2.5 millimeters. That's not a bad choice, to be honest. 3 is probably a little thick. 2 is probably a little thin. I'm going to go with their default. I'm going to say 2.5 is cool. Checkbox. I have now made a hollow nose cone. That's going to be designed for a BT-70 payload bay. This particular nose cone is 275, I think, millimeters tall. So you'll have to look at your printer and see if it can accommodate that. You might print a smaller one, or maybe you'll have even more space. It depends on, again, your model printer. To get this part out, I click on the word part, I right click, I say export, I give it a name, VT70 nose cone, STL, fine resolution, download, export that out. Done. All right, that was a little more complicated, right? Did I lose anybody? How do you feel? Thumbs up? So-so, thumbs down? All right, I got at least one thumbs up. The last part is the most complicated. So let me see if I can't, I'm gonna share something else with you. Let's see, stop sharing. Let me jump over to Open Rocket. After our last session, we had designed a rocket using Open Rocket, and in that rocket, we actually had a transition piece. That transition piece has to take us from our payload bay, which is a BT70, a thinner tube, to a BT80, our booster, which is a larger diameter tube. Let me share my screen with you. Window. Okay, I'm going to open. Can everyone see Open Rocket now? It's hard. You're a tiny little screen on my computer, so shout out yes or no. Can you see my rocket? Oh, we just lost it, didn't we? I had it. It was sharing, and now it's gone.
All right, we can see it now.
Great. So what part am I talking about? I'm talking about this part right here. Can everyone see that part?
Yes, sir.
Okay, let's look at that in 3D. All right, zoom in, right? So the piece right here has a flat bottom on it, and it has a little shoulder that goes inside the body tube. It has this diagonal piece, and then it has another shoulder that goes into the upper body tube. Not sure how it looks best to look at it. Here you can kind of see it here. Now it kind of disappears, but you can see it's got the shoulder. But that's the part we're talking about building right here. So if I open up the transition piece, you can't see the window now, can you? You can only see the main window. You don't see the transition window function. Okay, it's okay. I just want to make sure that we are on the same page of what we're building right here. So that piece looks like it sticks up about an inch into the body tube, about an inch to the body tube. And it has a diagonal length right here that is, let's see, 50 millimeters is the height of our diagonal piece. And we have shoulders that are 25.4 millimeters on either end. Okay, so I'm going to go back to the OnShape now that I know what I'm building. And we're going to share that screen again. Let's see where I had it. Can you see my OnShape again now?
Yes, sir.
Great. I'm going back to OnShape button on the top left, the Create button just below it, a document. I'm going to call this my BT 70 to BT 80 transition. We'll sketch this out in the front work plane. Click front, square it up, click sketch button. Okay, so what we're going to do is we're going to do half of our BT 80 booster. So the BT 80, let's see which button was that. It's BT 70. Here's BT 80. Okay, we did that earlier for our centering ring, right? It was 27.7, was half of the inner diameter of 65. Is that correct? Inner diameter 65. Divided by 2 equals 32.5. Is that correct? So this is a BT80 body tube with my booster. The inner diameter is 65 millimeters, right? So we want half of 65. And that gives me 32.5. That's not what we used before, did it? Was it? I think we might have made a mistake earlier. Okay, so I'm going to go back to my OnShape. We're going to make a line. We're going to say 32.5. Okay, and that is going to be half of the part that slides into our BT 80. I'm going to go up at least an inch. So I'm going to go up 25.4. That's 35.4. That's 1 inch in millimeters. Enter. I do need a lip. If I don't have a lip, it's just going to slide through and into there. So I'm going to come out. I'm going to come out 1 millimeter and press escape. Okay. Now, if we have a 25 millimeter shoulder on either end and a 50 millimeter long transition, that's going to be what, approximately 100, right? 25 plus 50 plus 25. So let's go ahead and make this 100 millimeters. And this is going to be the part that slides into our BT70 payload bay. So the BT70 is what's the diameter of that one? That's 55.4. So 55.4 divided by 2. Was that the 27.7? You guys have your calculator? 55.4 divided by 2.
$27.5.
27.5. Okay. So it's going to be 27.5.
Yes.
Okay. And then we're going to have that come down, slide into our body tube by an inch, which is how many millimeters?
25.4.
Okay, now I don't really need a lip on this one. I just need to draw a line down to here, down to that outside of that 1 millimeter. When I did that, you see how I colored it in? So I have a 32.5 is half of the diameter going into my BT80 booster. That little 1 millimeter lip right there. Okay. Then I have 27.5 is half of the diameter going into my BT70 body tube, and it slides in an inch. Put it in, which means it's a solid shape. That's what we wanted. Green checkbox. Now remember the revolve tool. Okay. I'm going to click on the shape first. Click on the revolve tool second. And it says, I already know the shape. Now just give me the axis. Click on the word axis. There. And it makes my three-dimensional shape. Pretty cool, right? So at this point, I'm almost done, except that this is a solid piece of plastic. So how do I make this not a solid piece of plastic?
I believe it was called a bullet. Can't remember.
a CAD software package. It's called a slicing software. Every 3D printer has its own slicing software. The slicing software I like the best, and it works on numerous printers, is from Prusa. Prusa is a company in the Czech Republic, and it works on our Prusa Mini. And we have designed and printed plenty of rockets parts using our Prusa Mini. So let me go ahead and share my screen real quick with this Prusa for the kind of last step of this process. Okay, I'm hoping that you can now see the Prusa slicer. Is that
Yes, sir.
great? Okay, what I'm going to do next is I'm going to go on the top left, and again, every software that slices for every printer is different. Your printer, if you have one, came with a whatever software it recommends one, but this software can be used with more than one type of printer. But functions are almost the same. I'm going to click on the Add Part button. It's going to say I can read STL files. I see a transition, a nose cone, a centering ring. What would you like me to print?
Centering.
Okay, which is a centering ring. We can do more than one thing probably. Okay, I'm going to open that. It says I've loaded my centering ring. And in fact, I can drag this thing around because you know what? I need 2 of these. And so what I can do is I can add an instance of this. So we're going to have 2 centering rings because it takes 2 to get my rocket to go. Okay, let's add another part. Let's add our engine tube. Going to put it on our print envelope here. So there's an engine tube. It defaulted to printing it straight up, which is great. That's what we wanted. Add the part. Let's add our transition piece. Okay, we'll slide that over here. It still fits in our print envelope. It's going to print the flat bottom down and the hollow opening up, which is great. And let's see. Let's push our luck. Add one more part on here. Let's add our nose cone. Put it over here. And it looks to me like it all fits. Now I think I got blue because this is not fitting, so I had to slide it in. Now it's green, it's fitting. So I think for the Prusa Mini, my nose cone's too tall. I think this particular object was too big for this print envelope, so I'll delete that one out. But all these parts will print. So I have other 3D printers in my makerspace, so I'll just use a different one from that nose cone. Or now that I realize it's too big, I can go back in and redesign that nose cone. I don't want to make this workshop any longer, but again, I could go back into my nose cone, change the length of that one piece in my sketch file, and make it so it would fit. And at this point, I would just turn on my printer and send my file to it. This software is really cool because what it's going to do is if I go ahead and tell it, there's a little window my way here. If I tell it to go ahead and run this file, it'll actually generate the file I need. It'll let me preview the layers. It's actually generating it right now. Generating my parameters, my perimeters. Generating G code, and it's almost done. It's 90% done. It's actually producing all the code for printing all these parts. I think I gave it a lot to print, so. Slicing is finished. So at this point, I can actually go down and slide through each part. So it'll show you which parts are being printed and which layers. So there's a little button down here, and I can see it. It shows me the actual printer moving and printing those different pieces. It's pretty neat the way I can scroll through that. So if you look, here's the different layers being printed. And I can even see, like I said, I can watch the 3D printer nozzle move around by sliding these different sliders. So it's kind of cool to see how the printer is going to print these pieces out. This is called slicing software, and this is basically how it works. And this generates what's called G code, which is the code that controls how the printer moves. And there's lots of settings in it for, tweaking it however you like. All right, so that really is a crash course on how to use OnShape for designing the critical parts for your TARC rocket. I'm happy to entertain any questions you guys have.
Are we allowed to use any other 3D design platforms like, say Blender?
So Blender is a graphics program, not a CAD software engineering package. So I would advise against Blender. I would use Autodesk Fusion 360, Autodesk Inventor, Pro Desktop, Pro Engineer, OnShape. There's a variety of packages. I would try to stay away from things like, see, there's a really easy one that kids use often. What's it called? I mean, there's some packages. There's a Google SketchUp can create 3D objects, but it creates sometimes shapes that are impossible to print. So remember how the software, the CAD package, would color in a shape when it was like, oh, that's a complete shape. There's no gaps. Like Google SketchUp won't do that, and so it'll generate a 3D object that you bring it into the printer, and the printer says, I can't do this. There's problems. I'm gonna just squirt plastic in midair. I don't know how to handle a shape with errors. So
I use Fusion 360, so I didn't know if it was just like different if I was allowed to use other softwares.
Oh, allowed. You can use anything you want. Yeah, no, this is not what's allowed or not allowed. This is just an example because I don't have to go over software installation. OnShape is easier for me to teach because if you're on a Mac, I'm on a Mac right now. You're probably on a PC. You could be even on a Chromebook. And as long as you have a browser that's compatible and has a good enough graphics card, you can do 3D engineering without me having to worry about what software you're using. But if you have Fusion 360, I actually prefer that. That's my favorite one.
Yeah, because we have to use these Chromebooks that the school provides, and they don't handle 3D very well.
No, Chrome is not a full operating system. Chrome is a tablet operating system. It's like the Apple iOS on your phones or iPads. So it can't run full software packages, but you can do OnShape. It's not going to be very fast. If you have your own personal computer, it'll be faster than that Chromebook. If the school, like your robot team, has another computer that's a Windows or Mac, it's going to be a lot faster than a Chromebook.
Yeah, we have 2 Windows computers that we have access to.
Yeah, so you can use Fusion 360 if you can download and install software. It's not uncommon for schools that have PLTW, Project Lead the Way, to have Autodesk Inventor. Again, OnShape means that you can even do it on an iPad. I wouldn't want to do it on an iPad, but you could. It wouldn't be fun, but you could manage eventually.
Yeah, it's a browser design.
Yeah. That was a great question. Any other questions? Okay, if I went a little fast, you can slide back and watch the video. I do not believe that my videos are, well produced. They will cover the topic I'm talking about, but I'm sure that you can go to a variety of different places. Like OnShape has their own tutorials and training materials, and learn way more than I know about how to do CAD. But hopefully this gets you going. And thanks a lot for attending this session. I'm going to try to turn off the recording now.